Hello, everyone. Welcome you all to this Simulation and Testing Congress 2021. I'm Bhavaneesh Athikary, lead for Automotive Indo-Pac region, Hexagon Hemi. So today's topic or title is Enabling Cognitive Engineering through Virtual Lifecycle for Manufacturing, which I thought would connect well with the theme of this conference. Let me start by introducing who we are. Hexagon is a global leader in sensors, software, and autonomous technologies committed to empowering an autonomous future. As global leader in design and manufacturing, we expertise in connecting all stages of manufacturing lifecycle, design and engineering, production, and metrology. Each year, Hexagon technology touches 95% of automobiles produced, 90% of aircrafts produced, 85% of smartphones produced. Hexagon builds, on an average, 40 autonomous vehicles every month and supports 3,000 plus companies in ADAS and autonomous technologies. Before getting to the heart of today's discussion or presentation, let us understand what this cognitive model is all about. Or let us understand how human learning process works. When you want to learn any new skill or art, the first thing what you would do is to predict how that particular action would lead to, or what that particular action would lead to. So let's take an example of serving in a tennis game. So when you want to serve in tennis, you would want to see where the ball would land, where you want the ball to be landed, at what pace, in what direction, for that, what should be your arm length. So these are some of the prediction you would do before you start. Once you predict, that's when you act, that's you actually serve. So once you serve, you inspect on what has been done and make sure that if it was perfect or any correction is needed, that's where your continuous learning and incremental improvements come in. That's cognitive learning process for you. So we asked ourselves if this process can be leveraged to improve the products and processes. So in designing various products, let's look at it on how we can get this model here. From a product design point of view, initially you would start with predicting, that is more on the design and simulation aspects. For this example of a gear, you would want to see if functionally, if it's performing as is needed. So once you do the virtual simulations and make sure it is being designed for, and then the next step is to manufacture it. That is the action part. So once this part is manufactured, you would want to inspect and make sure that the prediction is in line with what has been made. So that's where you compare and the continuous learning and incremental improvements happen. That's called the cognitive engineering evolution. So this is our model. This is what we try to apply to our engineering domain. So if you look at smart manufacturing as such, so how does product life cycle of yesteryear or yesterday looks like? So most of the functions operate in silos like design, production, engineering, quality inspection, or delivery. Most are done in silos, and there isn't much of a digital thread or digital twins in play here. Maybe max you have a design twin. Even the linkage between different departments are mostly silos or just between one or two groups. But if you look at the digital thread of tomorrow, it's more like you have design twin, engineering twin, production twin, inspection twin, all connected through a digital thread. Similarly, the linkages between different departments are much stronger, where you have right information being exchanged between different groups at the right time. Now, before getting into the details of virtual lifecycle manufacturing, let's understand the motivation behind it. So this is a curve which most of you are aware of, the cost curve. We all know that 70% of the cost is allocated at the early stage of the design, that's at the R&D stage. So to take an informed decision at the early design stage, you would need a lot of information. That is where we talk about upfront simulation or pushing the simulation upfront, but that's not good enough. So we have done it enough. We want to improve the accuracy of information or content of the quality of that information. That's where the virtual life cycle for manufacturing come in. So what are the current challenges of the current product life cycle? So it lacks a complete and synchronized data flow. Digital thread is missing. Less or late knowledge about overall production cost, robustness, and manufacturing feasibility of assemblies. Heterogeneous software landscapes makes result transfer more difficult and even impossible in cases. That's where the solution we have, which is called as VLMA, Virtual Lifecycle for Manufacturing, this which enables you to connect the different steps and accommodate data exchange to connect the real world with virtual or digital world, communicating and feedbacking the right information to the right place at the right time. And that's how we impact the cost, quality, productivity, and efficiency. Let's look at the framework of virtual lifecycle for manufacturing. So the quality data management is the heart of this framework. So all the info from PLM, production or process data, physical measurement data, which is from metrology devices, and also virtual measurement data are fed in to the quality data management tool, where the visualization or analytics are performed to compare the virtual with the physical and make sure any corrective actions, if needed, are taken, and then that is looped. This is the overall framework of VLMA, or Virtual Lifecycle for Manufacturing. So let us look at it from an assembly process point of view. We have our virtual assembly mixed box, where PLM data, constraint information, clamping, measurement positions, metrology, physically measured data, and virtual data from simulation world are fed in. Eventually, a visualization and analytics would be performed to make sure that if there is any corrective action which needs to be taken based on the comparison between the physical and the digital data what we have, the corrective actions are then performed. Let's get into a real life example of reducing time to market or identifying final quality challenges earlier in cycle. If you look at this example, stamping tools are built, and then the part or a prototype is being stamped. Once the part is being prototyped, you use measuring devices or metrology devices to scan the whole part, and then you have a reverse engineering application based on which you come up with the CAD data, which then is used for virtual clamping and welding or all different sort of process applications, which is then assembled together to digitally assess gaps. And then it goes on a virtual loop of continuous corrections. So it's very important to consider the process effects into our simulations. So as you can see here, this is an example of a spot welding of a particular part, where because of which the distortion or the residual stresses are considered in the next level of analysis, or distortion from it are considered for dimensional tolerance effects. It's not just limited to just the welding process, but any joining process can be virtually evaluated, and then it can be compared with the physical world. Another important aspect is to make sure that the process parameters, variabilities are considered, and that is robust enough to dynamically varying process variables. Finally, you get it together in an assembly environment to make sure that you have a good fit and finish to make the best perceived quality of it, and also to address all the functional defects like or issues like bus squeak and rattling. Let's look into a iterative process of a full vehicle level where subsystem is considered. And then you learn about how these parts are joined together with the data from the PLM. This information and the process information are collected to put together into a virtual environment where you assemble these parts or virtually manufacture these parts and assemble them together using simulation technologies. And then this data is then compared with the physical measured data. And once you have those comparison visualized, analytics are done on those data, then you run on a virtual continuously improving loops. One more example from a gearbox design point of view, where initial structural performance is evaluated, noise and vibration simulations are performed. Post that, you do manufacturing simulations like simulating machining processes, which is then taken into machining of the actual gear or production of the part. Once the part is being produced, various optical measurement or tactile measurement happens, which then compared again with as is designed part, and any improvement which is needed are again then looked to include any variations. So even considering the latest or manufacturing technology like additive manufacturing, the initial design and cost predictions are done at the initial stage, which is then passed on to design and manufacturing of process simulations, which is done in the virtual environment. And then correlation with the scan data or computer tomography data is performed, and then a feedback into the design and process optimization happens in a loop. So virtual lifecycle for manufacturing can be applied for various engineering like cost engineering, design engineering, and manufacturing engineering to improve the efficiency and reduce the cost. So overall, this one platform helps you to bring cost prediction, design and manufacturing process simulations, and correlation with the scan data and feedback into the design optimization, all of these together in one platform, which helps you to ensure consistency, traceability, bring transparency of data, improve planning, and enhance product quality. So as Hexagon MI, we strive to get the physical world close to the digital world. That's been our aim. That's a quick intro to virtual lifecycle manufacturing. I hope you all liked what I presented. I'll be happy to address any question you may have. Thank you all.